continuing with the discrete variables, but we're going to look at what the expected value might be that you're going to get if you do something repeatedly. So the example that they start with in the textbook is rolling a die, and we know that the results that can exist are 1, 2, 3, 4, 5, and 6. So we would expect to get 1/6 of our rolls to be a 6. Now, if we consider only one roll, then the expected value is not something that you can sort of predict for one roll. What we can do is over a number of rolls, and the bigger the number of rolls, the more likely we can expect it to come out. But we would expect to get 1/6 of them to be a 6. That's their example. So if there are 120 rolls, we would expect 1/6 of those to come out as being a 6. So we consider this bit here, which says that 1/6 of, remembering that of in maths means multiply, so 1/6 multiplied by 120 is equal to 20. So 20 of those rolls, we would expect to get a 6. That is literally year 7 or 8 probability, nothing more than that. Okay, so the green, if there are n trials, so in this case 120 trials, and the event that we're interested in has a probability of p, so the event we're interested in is rolling a 6, has a probability of 1/6, then the number of times we expect that event to occur is n times p, 1/6 times 120, nothing more than that. Okay, so first, just a random question pulled out of the first part. This chapter is divided into 3 sub-bits. We'll just look at each bit now. So if we have 3 coins that are tossed, what's the probability that they all fall on heads? So there are lots of ways to think about that, and that's, well, any coin is a 50-50, but we need to get a head, and then the next one has to be a head, and the next one has to be a head. We can't have any other option than that. It's the only way through. So the simplest way to consider that one is just to say, well, we've got a 50% chance, or a 1 in, oops, I did that, a 1 in 2 chance to get a head in the first toss, and then we're going to multiply that by a 1 in 2 chance of getting a head again, multiply that, and 1 in 2 chance of getting a head finally. So therefore, there is a 1 in 8 chance of throwing a head. Now, there will be times potentially where you need to do diagrams like tree diagrams, which you've probably seen before, just short ones where it's things like, and I'll just draw a really small version of one here. You probably don't, you don't need to do it for this question, but the possibilities are a head and a tail for the first toss. Okay, and then your second one, you could have a head or a tail if it was heads first, or you could have a head or a tail if it was tails first. And then finally, you can have a head or a tail, a head or a tail, a head or a tail, a head or a tail. And it's these pathways that you go down. So you could say I go tail, tail, head, or I could go head, tail, head. Follow those pathways. They're the possibilities. And in this case, all of the probabilities are just 50%. So I'm not going to write them all in there. But every next move is a 50% chance of it occurring. So the pathway, and the only pathway that we're interested in, is the one that goes heads to heads to heads. Okay? And that one is going to be, we do a half times a half, and there would be half there. So we multiply along those to get the probability. If this question said, what is the probability that you get 2 heads and 1 tail, then there are more than one path that can occur. So if we want 2 heads, we could go head, head, tail that way. So that's this one here, head, head, tail. Okay. We could also go head, tail, head, which is the one below that. I'll keep doing that. Tail, head. Oops. And we could also go tail, head, head. So we could go tail, head, head. So there are 3 different pathways that would allow that to occur. So there'd be 1/8 chance of getting this. Oh, it's having fit today. There is 1/8 chance of getting all of those different versions. So there are 3 in 8 chances of that occurring. So you can work out your probabilities like that. This question, because it's all heads, there is only one pathway that's going to work. Okay, and we would go half times half times half is an 8. So if 3 coins are tossed 200 times, how many times would you expect them all to fall on heads? Well, so for part B, oops, change that back to bigger. Part B, we would have 1/8 times by 200, so 200 over 8, and you can simplify. That's as simple as that. So this is not really heavy, difficult maths, but just getting these ideas first will allow you to answer some questions as we go along. So the chapter then goes on and starts to actually talk about expected value more formally, and that says, well, what are you going to expect to get on average if you did something? So there's an example here of a spinner. You spin the spinner, and the question might be, on average, how many points did you expect to get for every spin? It's okay to be able to say, well, I'm going to expect, and if you have a look at their answer, without looking at how they did it, their answer is 20 points, yet 20 isn't one of the actual options. So it works like averages. It's like when you say, okay, the average number of goals a soccer player kicks per match is 1.3, and you know that they can't actually kick 1.3 in one match. The same with this expected value is effectively like the average or the mean. So the average points you'll get if you keep spinning that spinner is 20. How? Well, they're all equally spaced around that spinner, so the chances are in 4 rolls you'll get 1, 5, 1, 10, 150 and 115. So if you add them up, that equals 80 divided by 4, you get 20. Okay, so this hopefully is still nothing too drastic, but if we formalise it a little bit, because it'll then help us to go down further, the part that is here is just saying what we've really done is we've said, well, there's a quarter chance of getting a 50, there's a quarter chance of getting a 15, a quarter of getting a 10, and a quarter of getting 5. So if we do this sum by actually multiplying a quarter by 50 plus a quarter by 15 plus a quarter by 10 plus a quarter by 5, we get our 20, rather than thinking of it as adding up the values and dividing by how many are there. The reason why that is useful is if we had a spinner that was not equally spaced and the probabilities were different, you couldn't just add up the values. So if my spinner looked like this, well, that's not a very good thing to use. And it just had, I don't know, like, a more likely sort of scenario where that might be your 50 in there, and I don't know, 15 is more out here or something, and 10 is out here, I don't know, 10, 5, then the average or the expected value that you would get from that spinner is different to the other one. You would expect much lower because your chances of getting 50 is much smaller. Okay, so you can't add them up and divide them by 4 because their probabilities are different. So instead, we should use this method over here and just multiply the probabilities. Now, if you knew the sizes of those, you could work out what's happening there. So in the green, the very mathematical way of writing it, it tells us that the expected value, which is often written as this, with an E with the capital X, because we're talking about a variable that can be only certain values, and that's not just a, it's the variable, not the actual values itself, is equal to, and look at this, they use that symbol which is mu, and that is a symbol that is used for mean. Okay, so it's basically equivalent to the mean. It's equivalent to add them up, divide by how many are there, except in this case we know we have to actually think about probabilities because the chances of them being there isn't always going to be equal. And it's equal to the sum. Okay, so that's the sum, but the XIPI just means the value, the first value that can happen, times by the probability of that happening, plus the second value that can happen, times by the probability that that one's going to happen, etc. So it's separated out like this. Okay, effectively, it's just a very mathematical way of stating what's up here. Okay, so let's just have a quick look at an example of a question like that. So Lachlan randomly selects a ball from a bag containing 5 red balls, 2 green balls, 1 white ball. Okay, so there's different numbers, so we know that the probability of getting them is going to be different. He's allowed to take a number of lollies from a lolly jar. The number of lollies is determined by the colour of ball, and it's showed on that table. What's the average number of lollies that Lachlan would likely expect to receive? Okay, so he takes a ball from a bag that has 5 red, 2 green, 1 white. So there are 8 balls in the bag. Okay, so if we have the bag equals 8 balls, okay, the probability of getting a red, okay, probability of red is going to be equal to 5 in 8. The probability of getting a green is equal to 2 in 8. I'm going to leave it as 8. Sometimes it's easier in these questions to not simplify and keep your probabilities with the same denominator. Just easier sometimes. It might not make any difference in this question, but it's a good habit to help. 2 in 8 and 1 in 8. Okay, so they're the probabilities. Okay, it then says he's allowed to take a number of lollies from the lolly jar depending on what colour he gets. All right, so in the long run, they're the probabilities of getting a red, a green, or a white. So what in the long run is he going to get? In the long run, he's going to get 5/8 of the time he gets red, which means he gets 4 lollies. Okay, so we're going to times that by 4. So it seems a little bit interesting because we're not really using the actual, the red. The red is effectively equivalent to saying 4 lollies. So it could be a token rather than a red saying 4 lollies. So that is why we're multiplying by 4. Okay, we're going to have 2/8 of the time. We're going to get 6 lollies, and 1/8 of the time you're going to get 10 lollies. Okay, so we can, you'd use your calculator probably to save time, but we've got 20 over 8 plus 12 over 8 plus 10 over 8. Okay, so that's going to be equal to 22, 32, 42. Okay, so 42 over 8 lollies, and you can simplify that down to a value. Okay, so that's the process that's being used. Because the probabilities are different, we can't just add them up, divide by how many are there. But effectively, same sort of idea. The last bit they talk about, and they call it doing fair games. The reality is we very rarely play a fair game, but knowing what a fair game might be allows casinos, in a lot of ways, but things to be so that they know that they're going to make money. So a really classic example is the roulette wheel. The roulette wheel has 18 red numbers and 18 black numbers, and one of the things that you can bet on is whether it's going to be red or black. Okay, and the payout is like 1:2. So if you put $1 on red and it's red, they give you your $1 back and another $1. So you get $2. So you've made $1. If it goes to black, you lose your $1. So if that was how the game was played, all right, I know there's a bit of information that I haven't talked about here about the green number, but let's forget there's a green number. In the long run, 50% of the time you should get $1. You should win $1. 50% of the time you should lose $1. So in the long run, if it was just red and black, that game would be classed as a fair game. You're not going to win or lose in the long run. Okay. The reality is that's not useful for a casino. So there is another number, and I know that some of them have 2 greens, certainly, and some have 1, and that changes the odds dramatically. But it says, well, if it's green, then you're not red or black, so you lose. So it adds that 1 extra spot of losing. And you think about it, that makes 36, so there's 37 possible outcomes. Only 1 in 37 is like that special green where you're going to lose both times. But that makes a difference in the long run. Okay, so this says calculate the expected gain from this bet. Okay, so this says, I place $2 on red, I get $2 back. The same way I put $1, I get $1 back. It doesn't really matter. Okay, so if I want to know what the expected gain is, we would probably think, hang on, that's going to be not a gain, it's going to be a negative gain. It's going to be a loss. We're going to lose over time. Okay. What's the probability of getting a red? So the probability of getting a red is equal to 18, but it's not out of 36, it's out of 37. Okay. And if that's the case, we would get $2. Okay, so we gain $2. All right, and if we then say plus the loss, we can actually put as 19 because the green would be a loss as well. So we can say 19 out of 37 times we're going to lose, and we're actually going to multiply that by -2 because it's a loss of $2. Okay, so you can see that you could work that out. Ultimately, it's going to be 1 in 37 times you're going to lose $2. So -2 over 37. Okay, so if the same bet is made 100 times, what is the expected result? Well, we'd have -2 over 37 times by 100, which is -200 over 37. Once again, you can simplify that down, but that is how much money you would expect to lose over 100 rolls, 100 spins. Now remember, this is an expected average over the course of the time. Now, in reality, we know that probability means that each individual spin is separate from the previous one. So it's going to be around about that sort of value. If you did it 1,000 times, it would be even closer to the correct value in theory. The more times you do it, the closer it's going to get towards that expected value. Okay, so that would be in dollars. It would be a loss of, what's that, 40, so $5 something. $5.41. So $5, that you would lose over 100 spins on average. Okay, so for a casino, that is not a great return for someone sitting there for $100 spins. Okay, but casinos don't only make their money that way. They make their money selling drinks and all that sort of stuff. On top of that, there are lots of other bets that can be placed. You can bet on a particular one coming up and you get a massive return for it. The chances of that happening are very, very small. And the person that sits there for 100 spins is likely to go, oh, I'm just going to have a go at this one. I'm just going to have a go at that one and lose some money otherwise. So it's a way of potentially keeping people around for doing it. They do also have some rules because it would seem like a really good plan at the casino to say, right, what I'm going to do is I'm going to bet on red. And if I don't get it right, I've lost $2. So then, as long as I've got enough money behind me, I'm going to say next time I'm going to bet on red again, but I'm going to put $4 in it. Okay, and then if I don't win again, the next time now I've lost all this money, but I'm going to put the equivalent amount of money and keep going until I win. And when I win $2 overall. And I start that process again. I keep doing that process. Sounds good. Everyone goes, oh, I'm going to make it. But the problem is that casinos put a limit. They put a cap to how much you can bet on it. So, yes, it seems like a good idea. Plus, they'll probably kick you out and say that they don't want you to do it. But if you, by chance, which will happen on occasions, get up to that cap, you've then lost $100 or something you can't get back because you can't bet any higher. So, that they are, cleverer than that, which is the point of it. Okay, so there are 3 little sort of sub-chapters, whatever this is, 7C, so 7C, 1, 2, and 3 or something that go through that. I like to think you'll find them pretty straightforward, okay? You can have a look at how they set things out. You can look at, more simplified what I've done, but just make sure that you can understand those questions.